Hello everyone, my name is Daan Camps and I'm a postdoc in the Scalable solvers group. Today I want to talk to you about FunFact, which is a Python package that enables users to build their own nonlinear tensor decomposition models. So first things first, what is a tensor? A tensor is a generalization of a matrix and a vector to higher dimensions. Where a vector is one-dimensional, a matrix two-dimensional, a tensor can be of arbitrary dimension. So for example, 3D or higher. So it's a way to represent multi-way data. Tensor decompositions are factorizations of these data set, and they have a variety of applications and use cases. For example, image and video compression can be done through tensor and matrix decompositions, and we'll give an example of that later in this talk. Another example is in unsupervised learning or blind source separation methods. For example, here we have a time series recording of an EEG data set from an epileptic patient undergoing an epileptic seizure. And decomposing this data tensor into factors allows one to localize the onset of the seizure in the brain. So this is another application. And then a final example that I want to highlight is in quantum physics, where tensor networks can be used to represent quantum states on classical devices that cannot be stored in a dense factorization or stored classically otherwise. So it's a model, a very useful model in quantum physics as well. So there's this whole zoo of tensor decompositions out there. For example, we have the singular value decomposition. For matrices, we have the generalization of that, the tensor rank decomposition for higher order tensors, a Tucker decomposition of higher order tensors, and then all kinds of tensor network models. This list is definitely non-exhaustive. There's way many more options out there. And with all these types of decompositions comes a whole array of algorithms to compute them. Some of them have multiple options to compute them. Some of them are very specialized. For example, SVD is always used with a bidiagonalization approach. Alternating least squares is a popular algorithm for tensor rank decompositions, and so forth. So the key message here is that every one of these decompositions requires a specialized algorithm to compute them. Furthermore, all of these models require and impose linear contractions between the factor tensors. So all these operations are standard inner or outer products. So it's standard contractions. So if we represent the whole universe of all possible decompositions of some data tensor as this green blob, then the ones that impose the linear contractions between the factors are actually a very small subset, and we haven't fully explored the full space or appreciated these generalizations so far. So I want to motivate this with a thought experiment. Suppose you have some data tensor labeled here as the cube with the label X, and you know, if you have a hunch, a good idea, that it can be very well approximated with a model of this shape, where this G and this F are some nonlinear functions which enrich the tensor model and can allow for a more compact representation. This is not like an off-the-shelf tensor decomposition model. So how we would traditionally go ahead to compute something like this, you would have to analyze this model, maybe compute its gradients. Based on this analysis, formulate and implement an algorithm, and then validate the results that you get from this implementation and analysis. So this is a time-intensive and a work-intensive process that can take many days, weeks, maybe even months or years, depending on the complexity of the task at hand. And it requires a lot of expert knowledge to complete. With FunFact, on the other hand, the user can just write this model as a nonlinear tensor expression and immediately use FunFact to factorize the data and validate the results. So this becomes instead a process of just minutes or hours, and is accessible to almost everyone. And it reduces the time to an algorithm to almost instantaneous instead of a very intensive process. Okay, so I want to say a few words of how FunFact achieved this and what's going on behind the scenes of the software package. So on the front end, FunFact provides users with a tensor algebra language, which is an embedded domain-specific language. It's embedded in Python, and it combines elements from the NumPy API with generalized Einstein notations. For those who are not familiar with Einstein notations, I've given a simple example on the slide. So here on the left-hand side, the boldface symbols are tensors, and the subscripts are indices or modes of these tensors. So for example, this tensor A has two indices labeled I and J. So this is a matrix, a two-way array. The B tensor has just one index, so this is a vector. And then in an Einstein notation, it is assumed that indices that are repeated in a binary operation are contracted over. So this J index is contracted over, and the result is some other tensor C, which just has as the index I remaining because it has been contracted over. So this is just a shorthand notation for something like this, where we write out the explicit summation over J. And FunFact will use this type of notation extensively in its language model. So on the back end, FunFact is built on top of modern numerical linear algebra libraries that support automatic differentiations, such as JAX and TensorFlow from Google and PyTorch from Facebook. Another backend that we support is the NumPy backend, but this one comes without automatic differentiation, so it can only be used for forward evaluation of your model. And then the workhorse algorithm that is achieving all of this is a variant of stochastic gradient descent with multi-replica learning. So with multi-replica learning, I mean if like you want to approximate or compute a Tucker model, which can be represented like this, FunFact allows you to initialize a whole array of these models with all random initial guesses and optimize them all in parallel and return the best solution that it's found. Okay, after this look behind the scenes, I want to give you a brief flavor of how you can use FunFact with a kind of hello world example, a very simple use case. So a first step would be to install FunFact from the Python package index and load it into your Python environment like this. After you've done that, you can declare some tensors and indices. So we have two tensors A and B here, and three indices I, J, K. And then we can use these objects to write a FunFact tensor expression. So this is a rather simple tensor expression where we compute a contraction between A and B over the K index. So this is an Einstein notation because the K index is repeated on the left-hand side and the right-hand side of this expression. So this is just a matrix inner product and can thus be seen as a low rank, a rank 3 approximation for a 50 by 20 matrix. And when you write this tensor expression in FunFact won't do a lot of calculations in the backend yet. Instead, it relies on a lazy evaluation model. It will store the abstract syntax tree of this tensor expression for when it's actually used in future calculations. So when it's used, for example, in our factorize method. So we can load some target data and then immediately use our factorize method to optimize this tensor expression for the target data and find a low rank approximation of this target data. So it can be used in just a few lines of Python code. To illustrate the strength and flexibility of the language model that we introduce, I'm going to highlight a few well-known tensor decompositions and show that they can be written in just 1 or 2 lines of FunFact code. So the first example is a Tucker decomposition where we have a lower dimensional core tensor, which is blown up to higher dimensions with some autoproducts of some factor matrices. And this can be written in a FunFact tensor expression like this. Another well-known and widely used model is a tensor rank decomposition, which can be written in a FunFact tensor expression like this, where we have used this index decorator. The exact meaning of it is not important, but it's an addition to enrich our language even further. And then another final example is a tensor train decomposition, where in this picture we have six tensor cores, which corresponds to the G1 to G6 tensors here. The R indices are the inner indices, which are contracted over, and the I indices are these outer legs. So these are the surviving dimensions of the tensor train. So this is a 6-dimensional tensor as a result. Okay. In the second part of my talk, I want to give 2 example applications that we can do with FunFact. I can run with FunFact. The first one is about image compression with nonlinear factorizations. So in the linear framework, it is well known that the SVD, the singular value decomposition, gives the best rank R approximation to a matrix. So if we have some matrix M, which represent our image, and we compute the singular value decomposition, and we truncate it to the first rank R terms, we're guaranteed to have the best representation with R ranks. And if we use the standard NumPy SVD algorithm on this example image, and we truncate its SVD to 24 ranks, we find an approximation like this, which is still visually very good. The mean squared error loss is given below the image. We can truncate further to 12 or even 6 ranks, and we see that the image quality degrades and the loss increases. A first interesting observation is that when we switch out the special purpose NumPy SVD solver and instead use FunFact and write a low rank tensor expression to factorize this matrix, we find the exact same result. So the loss is exactly the same as before, and visually the images are given the exact same approximation. So this is already a nice observation, but we've discussed, as we've discussed before, FunFact allows for more general models to be evaluated on our data set. So we can go further and write something like this, a nonlinear tensor factorization or matrix factorization expression in terms of a linear combination of radial basis function kernels. More about this method can be found in this paper. The key here is that this model takes a linear combination of these type of factors, and this is requires as much data, like one of these terms requires as much data to store as one order product, standard order product of 2 vectors. Instead of a standard order product, we have like an element-wise subtraction, and we apply this nonlinear transformation to the result. So the data complexity is the same, but the model is richer because of the nonlinearities and the increased generality. And we see that if we optimize this type of model to our data, then with the same number of ranks, we actually can achieve a lower loss function compared to the SVD. And also visually, the image approximation is better, close to the original. This becomes clearer when I put them side by side. So on the first row, we have the result with the singular value decomposition. And on the second row, we have our RBF approximation. And we see that the loss on the second row is always lower for the same amount of ranks, and that the visual representation is more acute. The details, for example, in this 12 rank case, the details are more acute here than on the first row. A second totally different example application that we can do with FunFact, and we can try to solve with FunFact, is quantum circuit compilation or quantum circuit synthesis. And this is the task of finding a quantum gate representation for a given unitary operator. And this is a problem which can be solved as a tensor decomposition problem. Assume that we have some unitary UN, which acts on n qubits. So it's a 2 to the power n by 2 to the power n matrix. And we want to evaluate this or run this unitary on our quantum computer. This is actually not directly possible because quantum computers only work on 1 or 2 qubits at the same time. So this unitary has to be decomposed in smaller, simpler gate blocks, which is represented in this diagram. So this problem is the quantum circuit synthesis problem. If we now look, for example, to the quantum Fourier transform, It is well known that for an n by n matrix, the quantum Fourier transform can be applied in log n squared gates. This is a theoretical result, and I've drawn the 3-qubit quantum Fourier transform circuit on the slide. And we see here that there is some interactions between qubit 0 and 2, for example, in this gate and in the final gate. And this might be something that cannot be run physically on a quantum hardware because it might not correspond to the topology and the connectivity of the qubits. So the simplest topology that all devices support is a nearest neighbor connectivity between the qubits. So we have, in this case, we would have to resynthesize or recompile our unitary to a quantum circuit structure that has nearest neighbor connectivity. So an example circuit like this could be feasible to run on hardware. And we can actually compute something like this with FunFact. So with this small function, we can generate tensor expressions to represent 2-qubit gates. So we declare a tensor, a 4x4 tensor, which is a 2-qubit gate with some unitary penalties on it. And then we compute the Kronecker product of this 4x4 tensor with the identity matrix to place it on the correct qubits. And then the whole circuit becomes the matrix products of 6 of these 2-qubit gates. So this is a complete tensor expression representation for this type of circuit. If we put this in our factorized method, this circuit that we've generated and optimized for the 3-qubit QFT matrix, we find that we actually can achieve a very good approximation. So the loss becomes very small, and also the penalties on the factor tensors, the 6 2-qubit gates, becomes very small. This is also shown in the picture on the bottom, which shows the inner product of all the factor matrices with themselves. So if they're unitary, they should be the identity, and then the scale of these images, they all agree very nicely with a diagonal matrix. Okay. So before concluding, I want to acknowledge the team that has been working on this project. So FunFact has been developed in collaboration with Yuhang Tang, also from the Scalable Solvers group, and previously Lisa Rybova also worked on this project. It's funded through an LDRD grant. And now to conclude my talk, I want to recap that FunFact is a rich and flexible language to write nonlinear tensor algebra expressions. It can immediately solve the inverse problem thanks to modern NLA backends like JAX and PyTorch, which dramatically reduces the time to algorithm to try out and factorize new tensor decomposition models. We just released our software under version 1.0 RC. You can find out more information about the software on these links, 3 links out here, and we're actively looking for more users and more ideas for applications. So don't hesitate to reach out to me. We can have a chat about it. With that, I would like to thank you for your attention and let me know if there are any questions. Thanks.